Swayam Prabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in this MOOCs course, Power Plant System Engineering. Today we are going to start the module 2, and in this module we will discuss about vapor power systems part 1. So, in the first lecture of this module, I will try to explain the following topics. First is vapor power plants, its basic introductions. Next point would be the performance indicators for vapor power plants. Here we will try to see for a plant designs what are the critical thermodynamic parameters that needs to be evaluated first. Then we will move on to thermodynamic analysis. Here we will mainly focus on the steady flow energy equations which can be applied for a simple vapor power plant system. Then we will try to revisit our basic thermodynamic aspects that talks about Carnot cycle, and in fact Carnot cycle or Carnot engines is one of the fundamental cycle in which we can get the information of a net work output for a given heat inputs. In other words, it justifies this fact that it is possible to extract work output from a low grade energy source which is in heat form. But unfortunately, there are certain limitations. Carnot cycles cannot be implemented in practice. So, why we cannot implement Carnot cycles, we will be discussing about that topic. Then if Carnot cycle is not there, then what is the next alternatives? So, for that we need to consider certain power plant design considerations. Based on that, we will propose a new cycles which is in line with the vapor power plant systems. So, this is the overall summary of the lectures. Then let us start the basic introductions of vapor power plants. We all know that energy is the basic need for society, and in fact in 21st century there is an immense growth of power that needs in every sectors across this globe. In fact, there are some main areas of this application is that if you want to extract power, then the possible choices that we can have is through internal combustion engines or gas turbines power plants, or third category would be vapor power plant systems. So, in our basic thermodynamics course, that is applied thermodynamics course, we have mostly dealt with internal combustion engine and gas turbine plants. Of course, to some extent we will also discuss about the steam power systems, and in this module we will exhaustively discuss about this vapor power plant systems. Now, the main basic difference between this IC engine or gas turbine plants with respect to vapor power plant is that in IC engines or gas turbine systems, the main working fluid is always remains in the gas phase. So, for example, either you see internal combustion engines where we think about only air or air fuel mixture, or even in gas turbines air is the basic ingredient which is sucked into the intake systems of a compressors, and in this entire cycle the working fluid is always remains in the gas phase, although its pressure, temperature keeps on changing, but the working fluid remains in the gas phase. But in a vapor power systems, we dealt with the working fluid which continuously changes its state, thermodynamic states. So, in other words, what we say that the working fluid is alternatively vaporized and then condensed. So, for that things we need a large volume of working fluid or large quantity of working fluid. So, for which water is the unanimous choice. Now, while looking at these vapor power systems, if you want to convert the water to steam, then we require some heat from a reservoirs. So, regardless of what working fluid we use, the choice of heat transfer is mainly decided by the user. So, this can be a conventional fossil power based systems, or this can be like coal. Other things, this choice could be in a nuclear mode, or it can be in any other oil, or nowadays the renewable form of energy also comes into pictures. So, the choice of heat transfer mode to the working fluid, it can be biomass, solar or geothermal. But whatever heat source you precisely decide, it all precisely depends its availability at that locations. So, here we are going to demonstrate a schematic diagram of a vapor power plant systems that talks about the complete pictures. So, what we see here in this figure is that we have a boiler, we have a turbine, we have a condenser, we have a pump. This is the main constituents which comes under the segment N, and beyond this N we have another segment that how this boiler gets input, gets heat from the outer source. So, that segment is N. So, that means M is stands for the supply of energy to the working fluid. So, it could be a fossil fuel, it could be a nuclear, it could be a solar, it could be geothermal unit. Geothermal unit mainly talks about inside the earth, the temperature medium is very high. So, we can think about extracting energy from the underground earth materials, and that can be pumped as a hot water and steam through the heat exchangers. So, other option could be a solar thermal based vapor power plant where boiler is integrated with a solar power systems. Other option is that we can think of a nuclear power plant where boiler is integrated with a nuclear reactor. So, this choice of the energy or heat energy supplying to the systems is mainly based on the users. The second category which is in the N, which is means that it is the energy conversion mechanisms. That means, when heat is being supplied, we are trying to find out a mechanism through which we can get work. So, this has something as resemblance that the working fluid is being circulated in this circuit which involves N, and that takes heat from this boiler and which can quantify it as a Q1. And if you look at this Carnot cycle, which sees that we have a source, we have a sink, and this source and sink are operated at certain temperature T1 and T2, and this is connected to a through an engines involving an working fluid. So, in this process the engine takes Q1 amount of heat and rejects Q2 amount of heat to this sink, and side by side it produces net work W net. So, if this is the case, then if you can imagine this particular cycle which is N, which involves as a engine, which replicates as an engine. So, in this process heat is being supplied to this segment N, and heat is being taken out in this condenser. So, this we can say as Q2, and this Q1 is being heat supplied by the fossil fuel into this system N, and through this process this turbine delivers W net. So, this is a direct resemblance that how a vapor power cycle concept comes from the Carnot engines. Now, apart from this, we have another segment called O, that means when the turbine gives power output, net power, then it has to be integrated for generating the electric power. So, there is an electric generator or alternator. Other part is that which is P in this segment. Now, in order to run this system N, we require continuous supply of working fluid. That supply we are getting it through a feed water pump which is used, and in fact, it takes water either from a sump or it can be taken from a cooling tower. So, it all depends how you supply working fluid to this subsystem N. So, this is how the entire vapor power plant system consists of, but our main focus would be in this section N or subsystem N. So, and we will not deal with how this heat source comes. So, we will simply say that it is a fossil power based power plant system when water is getting heated, and we will say that water is being supplied either from a river or from a sump, and or it can be recirculating water from a cooling tower. And the other part is that in terms of power generations, we will not think about the electric power, we will just talk about only mechanical power, which is the net work output. Now, let us try to understand what is this W net. So, in this Carnot cycle, we says that what that is a net work output that gets out of the systems. Now, here I am just explaining that how that net work comes into pictures. So, normally when an engine is operated, we say that the ideal component would be a turbine that produces power net work output. But again, there are some additional devices which needs to be integrated in this thermal circuit that also consumes power. So, in this case, in a vapor power system is simply a pump. So, the net work is normally decided by turbine work minus pump work difference. So, this picture shows about how that concept it is justified. So, it means that if you still recall, and second point that I need to emphasize, what is the actual cycle and what is the Carnot cycle. So, what does this mean? If you look at two engines, one is a reversible engine or other is any arbitrary engine X, and they operate between two temperatures, upper temperature TH or source temperature TH and lower temperature is sink TL, and both operate in the same temperature limit, and in this process the reversible engine produces work output as WR, and any other engines arbitrary engine it produces work output is WX. So, obviously, since it is a reversible engines, we can say it is a Carnot engines and its efficiency is decided by this Carnot efficiency, which is if eta C is equal to TH minus TL by TH. And if you look at the other engines for which the net work is normally decided by this WX. But what the next figure talks about, that we can think of a systems or imagine a systems that instead of talking about this heat, and we will simply remove the source and connect these things, that means through this manner. So, in that way what we will have is that some work is being utilized to run these reversible engines. So, basically what we are seeing is that this net work, for example, if you remove this reversible engine by a pump, so obviously it will take some work input which is WR, and it operates from same source TH, okay, and they take both Q1 and is heat input for both of them. And if you imagine that we do not have these reversible engines, and instead of that this reversible engine to produce this net work, we also require some additional components, that is W pump. So, instead of WR I will put it as WP, so that the net work we can imagine to be WX minus WP. So, the net work now comes down as the actual work minus the pump work. So, here this actual work refers to our turbine work. So, what it trying to say is that not all engines are reversible. So, for any irreversible engines, the efficiency will be always less than the Carnot efficiency. So, this is in the same concept. So, the basic summary that we get out of this exercise, that all real processes are irreversible and this irreversibility reduces the cycle efficiency. Now, using this concept, we will move further to find out different performance indicators for a vapor power systems. The first performance indicator is nothing but the efficiency ratio. Now, again we revisit the same Carnot cycles, which we call this engine is being operated through a cyclic device, and it takes QH amount of heat and rejects QL amount of heat. But in the source, while producing this, how this QH is coming? QH is coming from the fuel air mixture, which is being supplied at a source segment, and side by side it gives the combustion products. So, what we are trying to look at is that there are two efficiency that is coming off. One is the Carnot efficiency, other is with actual engine's efficiency. So, when I write this Carnot efficiency, which is eta Ti, which is thermal efficiency for a Carnot engines, that is 1 minus TL by Th. Now, if you talk about the actual engines, so that is nothing but the W net by Q in. So, one parameter that can be popped in, that is because due to irreversibility in the medium, or in other words, if there are irreversibilities in these systems, then our efficiency cannot approach to this Carnot efficiency. So, for that reasons we define this efficiency as actual efficiency. Now, looking at these two efficiency, because Carnot efficiency will talk about the upper limit and actual efficiency will talk about the system operating in while calculating irreversibility in the medium. So, ratio between these two, we define it as a efficiency ratio. This is something similar to the second law efficiency, what we understood in the first level thermodynamics course. Then moving into next parameter, which is work ratio. As I mentioned earlier, this net work consists of two parts, one is turbine work, other is the pump work. So, difference between these two, we call this as a net work, but gross work which is defined by the turbine work. So, work ratio is defined by net work to the gross work. So, W net by turbine work. So, many books also refers that instead of talking about work ratio, they talk about back work ratio. Back work ratio means it is not in the form of net work, it is in the form of pump work. So, basically pump work is the additional input that we are going to give this engine to produce the turbine power. So, back work ratio is normally defined by pump work to the turbine work. But however, our attention will be mainly focused on the work ratio. The next important segment of our topic is the performance indicator is the steam consumption rate. So, to quantify this, we call this as a specific steam consumption or heat rate. So, what does this mean? So, when you say work ratio, the normally it defines is the size of the systems, and it is more or less we will talk about the what should be the size of turbine, what should be the size of compressors, and which involves the capital cost. But to have this, once we have installed this turbines, compressor and other units, but we need a continuous supply of working fluid. Normally the continuous supply of working fluid is decided by the fact that how much steam is being fed to the turbine to produce certain work output. Or in other words, when you are talking about steam flow rate, that can be quantified as also heat rate. So, these two parameters talks about the running cost of a plant. So, for that reasons we define these parameters as follows, that the direct indication of vapor power plant is given through specific steam consumptions. It is nothing but the mass flow rate of steam per unit power output. And in analogous to this, we also call as heat rate, which is the amount of energy added by heat transfer to the cycle to produce a unit of work output, that means in kilowatt hour. So, if you compare the SSC steam consumption, specific steam consumption and heat rate, we will have a direct relations, but it has a inverse relation with respect to efficiency. So, many times if you bring back the definition in mathematical form, we say specific steam consumption SSC is 1 by W net and its unit will be kg by kilowatt second. But what happens is more appropriate way of looking at, and this number is typically very low. So, a more appropriate way of looking at to define the steam specific steam consumptions in terms of kg per kilowatt hour, because kilowatt hour is a unanimous choice in terms of recognizing the power. So, for that reasons the SSC is equal to 3600 by W net. So, this 3600 term comes when you convert hour to second. Now, once you know this steam consumption rate, then the corresponding correlated parameter would be heat rate, which is nothing but how much the amount of energy is being supplied per 1 kilowatt power. So, each heat rate is proportional to Q in, or in other words heat rate is inversely proportional to the thermal efficiency. Now, moving further, we will talk of more details on thermodynamic analysis, and this thermodynamic analysis is mainly dealt with the steady flow calculations. We all know precisely that steady flow energy equations is one of the fundamental equations that was taught in the level 1 thermodynamics course, and we are going to use those steady flow calculations for a vapor power systems. If you take a vapor power cycles and we try to understand that cycle through steady flow energy equations, then certain characteristics features that we can highlight here. First, the working fluid is a condensable vapor which is liquid phase during one part of the cycles. So, working fluid at some part of the cycles remains in a liquid phase and we can condense it, and this liquid is obtained through condensation. The cycle consists of the components like boiler, turbine, condenser and feed pump. Boiler supplies heat energy to the working fluid, turbine produces work output, condenser condenses the steam to water, feed pump supplies the working fluid of required volume, and each component consists of a open system. They are connected in series. We will see that how they are connected. The working fluid passes through each component and changes its phase. The working fluid enters and leaves the system in the same state. That means, it enters in liquid state and also leaves the systems in the liquid state. We will see how it happens. The work and heat transfer in various processes of the cycle is calculated through steady flow energy equation and it is calculated based on unit mass. The changes in the kinetic and potential energy of the fluid at the entry and each component is neglected, and all the processes are assumed to be reversible. So, it is an ideal cycle. The component as well as this system analysis can be done through steady flow energy equation and the first law of thermodynamics. Let us understand how these steady flow energy equations are obtained. So, we see here that the components like boiler, turbine, condenser and pumps in this circuit, heat is being given by a boiler, work is being produced by a turbine, pump supplies the necessary pressure difference between condenser to boiler, and steam that leaves from the turbine it gets condensed in the condensers. So, we can see here that the working fluid enters to the systems, that is state 1, it is in the liquid state, that means through the pump it is a liquid state, and when heat is added it changes its phase. So, it becomes steam. So, it enters to the turbine and again after coming back again when it enters to the condenser, it releases its heat and gets condensed, again it comes back a water medium. So, it means that it enters and leaves with same state, that is in the liquid state. There are two options possible. One is we can think about this working fluid continuously supplied in a cyclic manner. Other option is that in many a times, since the working fluid is water, we do not circulate it. In one way, that it comes out from the condenser and goes to the atmosphere, rather we take fresh water from the atmospheres. So, the state A dash and A, they are we have introduced here, but their thermodynamic conditions may be little bit different, but any case they enter in same state. But what is main difference is that same system which was a closed system, it is now viewed as a open system, because the circuit breaks here. But however, if you do the steady flow energy calculations, it really did not alter the main energy equations. Now, if you recall the main steady flow energy equations by involving heat transfer, mass transfer and enthalpy difference, what kinetic energy changes, potential energy changes, what we assume is that since it is a power producing device, we will neglect the changes in the kinetic energy and changes in the potential energy. So, these two terms gets neglected in comparison with this enthalpy term, because this contribution of these two is very less as compared to this enthalpy difference. So, the main equations boils down to Q dot plus W dot is equal to m dot into H2 minus H1. Now, this equation is being applied for boiler which supplies heat, turbine which produces power. Of course, the state points are different, here H2 minus H1 and here H3 minus H2. Again in the condenser, it is again it is a heat rejection process. Feed pump also is the enthalpy difference. Now, if you sum it up, one fundamental thing that arrives here, that cyclic work transfer and cyclic heat transfers are same. Now, again if same system is viewed as a open systems, that means fluid enters at a state A and leaves at state A dash, here also we will have the same thing, but by assuming this difference and this difference to be small, this also talks about the same information, that summation of Q and plus summation of W is equal to 0. Okay. So, this is all about the thermodynamic analysis, where we did not bring the efficiency parameter into this picture. Now, we will move on to the fact that when you think about a Carnot cycle, why we say always repeat the word Carnot cycle, because the first basic important information that Carnot cycle gives is that thermodynamically, if you want to extract heat from a low grade to high energy, that is in the heat form, to convert heat energy to a work form, then we must reject the heat. And this sense was visualized by looking at the components which we can act as a boiler. Now, instead of the turbine, because the turbines was the recent development, but initially in the Carnot cycle it was imagined to be an expander which produces the power, condenser which releases the heat, boiler it takes the heat, compressor which feeds this working fluid to the boiler. And same thing if you want to draw a plot in a TS diagram. Ideally speaking, this is the TS diagram. If you look at the working fluid, there is a dome, and in this dome you can say this is the critical point and this side is liquid, and in between the dome we have liquid plus vapor, and outside the dome it is the vapor. So, the circuit starts with point 1, where heat is being added through a boiler, that is process 1 2, and process 2 3 is in the expander W23. So, here Q12 is added and here W23 is getting produced, and heat rejection process, that is from 3 to 4 in a condenser. So, it is a Q34 and compressor takes W41. So, based on this we can recalculate these equations Q12, W23, Q34 and W41 based on this easy calculations, where m dot is the mass flow rate of the working fluid. Then let us understand, although thermodynamically it is possible and we can draw this in the TS diagram, but unfortunately if you look at the close realistic way of applying this concept, it is not advisable to operate a vapor power system on a Carnot cycle. The main difficulties are as follows. First thing is highest possible temperatures. The highest possible temperature of the working fluid is decided based on the metallurgical strength of the turbine blades or in a expander. Lowest temperature is mainly dealt with, that is in the condenser side, it is mainly dealt with the water availability in the atmosphere or river and some which is in the range of 15 to 25 degree centigrades. Other option is that now to for a sufficient sucking of water or supplying these things, we need to have a temperature difference of 10 to 15 degree Kelvins. So, in other words, it says that the condensing temperature should be in the range of, ideally should be in the range of 25 to 30 degree centigrades with an average condenser pressure of 0.04 bar, which means if you want to try to plot them, take a data and try to calculate them, what we says is that when you see efficiency and if you say that a precisely working pressure for a boiler is 30 bar and condenser pressure of 0.04 bar, we need to find out, we can see that your efficiency increases with condenser pressure or temperature, which means the efficiency increases with decrease in the condenser pressure. If this side is a decrease in, that means 0.75, 0.5 and 0.25. So, the efficiency increases with decrease in the condenser temperature, but again efficiency increases with increase in the boiler pressure. So, these two things are contradicting to each other. Side by side, if you talk about the steam consumption rate, specific steam consumption, it increases if your boiler pressure increases. So, a proper overlap or matching has to be done to precisely say that what should be the upper limit of boiler pressure and what is the lower limit of condenser pressure, and it more or less boils down the range between 30 to 35 bar for boiler and 0.0405 bar for condenser, have a reasonable estimate. Another limitations that a Carnot cycle has is that it has the highest possible temperature is 374 degree centigrade and 221 bar. Through that we can operate the Carnot cycle in the wet regions, which is somewhere here critical point. With respect to Carnot cycle, we can operate these things in this particular range. And even this Carnot cycle has work ratio of 0.07, which is not advisable, and if you include this component irreversibility, this number still falls down. In addition to that, there are practical difficulties which is associated with respect to compressions when we deal with the liquid vapor mixture during the compression phase. That means, it is if you work this, if you find out, if you think about this compressing from 4 to 1 in this liquid vapor region, because this region is liquid plus vapor, then it is a difficulty for compressor, because liquids are vapors are two different states and they form actually a non-homogeneous mixture. And moreover, if you look at the power output thing, power input from 4 to 1 and power output from 2 to 3, more or less this is a rectangle and more or less they have equal sides, which means to get appreciable power output from the turbines, we also expect that similar range of compression work needs to be there. So, which is not a feasible options. So, for that reasons the Carnot cycle was ruled out, and in that while ruling it out, what was the proposed is a Rankine cycle. So, what does it say? That if you look at a comparison of TS plot for a Carnot cycle and a Rankine cycle, both operate at same temperature limits, let us say TA and TB. While operating in same temperature limits, what we have done is a little bit, that means looking at the limitations of Carnot cycle, we have pushed this 0.4 to the saturated liquid regions. So, now 4 falls in this saturated liquid regions. And what did you do? Then you bring this state of 4 to 1 through a heating process, constant pressure heating. That means 4 to 5 process is the pump work, and through this process you can clearly say the side 4 5 is less than the side 1 4 dash. So, in that way we reduce the pump work drastically. But while reducing the prompt work, obviously then net work also gets increased. That is one part. Second part, through this process additionally what did you do? If you look at the area under this diagram, the heat input is little bit increased, but side by side for which the efficiency for Rankine cycle is less than the Carnot cycle. But if you talk in terms of work ratio, your work output for Rankine cycle is higher than the Carnot cycles. So, this gives a clear indications for a vapor power plant which precisely work on the work ratio enhancement rather than the efficiency. So, in through this process what additionally you do, size of the plant becomes relatively smaller because you have reduced the pump work as compared to this Carnot cycles. So, based on these considerations, we are now proposing a main concept of vapor power plant design considerations, which talks about two things. One is capital cost, other is the running cost. So, one is the capital cost mainly is the function of size and complexity, like what is the size, what should be the size of boiler, turbines, pumps and all, and this operating cost mainly depends on the overall efficiency, and that operating cost mainly assessed through the how much your steam is getting into the systems. So, the overall efficiency is a function of these two, like source efficiency through the combustions which is obtained by amount of available energy which is transferred as heat to the working fluid. Other is the cycle efficiency, which is the actual heat which is converted to the mechanical work. So, these two things has to be coupled. Now, here I want to try to emphasize a case study which talks about the main design aspects of a vapor power plant systems. What does it mean is that, so here we are proposing two important parameters or indicators. One is work ratio WR, other is the efficiency. And what were the user input? User input is the heat input Q in which is comes into this power plant systems, and what is the main need? We need to get out of main work is net work, which is the difference between the turbine work and turbine pump work. Now, we are proposing two situations, one is an ideal cycle, other is the actual cycle. So, actual cycle involves a component efficiency, or we say that which we call as process inefficiency or irreversibility introduced into the cycle. So, let us try to find out the first focus on the ideal cycles. So, for the time being just us not think about actual cycles. So, ideal cycle we have two models. One ideal cycle, one will be we can think of I will just say for a given work input of 150 and we are trying to get out of a number that W net is 49. So, that means we have resources available of Q in is maybe 150 kilojoule and net work is we are supposed to get as 49. So, through this process there are two possibilities, that means to get this 49 I can think of turbine work as 125 and pump work is 76, difference is again 49. So, these are just a generic numbers. In another situations I will propose the turbine work is 50 and pump work is 1. In both the cases your net work is 49. So, based on these numbers you can calculate the work ratio. You will find the cycle 2 has work ratio of 0.98 and while the cycle 1 has work ratio of 0.392, but both of them have same efficiency. So, what is the main summary that we get? So, is a cycle 2 is a better approach because it gives higher work ratio for same efficiency. And now, if you propose the cycle 2 and same thing we recalculate here for actual cycle, where the component efficiencies of turbines and compressor is introduced with a number of 0.09, then we can recalculate these numbers. Here also if you just decompose this ideal cycle to actual cycle, same logic also you will get. In one case we will have work ratio of 0.975, other case we will have work ratio of 0.25. So, obviously cycle 2 is also a better approach. Now, comparing this and these two, if you try to compare cycle 2 for ideal and actual, what we found out, we will find out that means when there is a minimal pump work, the work ratio is not much affected. So, of course, there is a little bit of difference in the efficiency, but with small difference in the efficiency, work ratio is unaffected, mostly unaffected. So, that is the reasons the ideal choice for a power plant consideration is to have minimal pump work, and which can give a very good overall efficiency and work ratio. So, with this background and topic, now we are going to solve a numerical problem. So, whatever we have understood in this lecture, if you want to quantify in a thermodynamic cycle, then let us see how we are going to do that. So, one particular numerical problems that we are going to look at is that the problem that is posed is that a power plant operates with upper pressure of 35 bar, which is on boiler, and lower pressure condenser is 0.04 bar, and it operates in a Carnot cycle. So, we need to find out work, heat transfer, cycle efficiency, work ratio and all. So, this is the similar problem that I have given in the case study, but here we will look into a realistic case, how actually by using the steady flow energy equation, how we can find out all these numbers. So, before you start the problems, we should recall that we must have a thorough knowledge of the steam table, because we have to take most of the data for this water and steam medium. So, first we will understand that what this Carnot cycle is all about in a TS diagram. So, we plot this in a Carnot cycle. So, state 1 2 is the boiler, 2 to 3 is the turbine, 3 to 4 is condenser, and 4 to 1 is pump. And we say that this saturation pressure and temperatures corresponding to this, we say it is a 35 bar and this is 0.04 bar, and corresponding temperatures we can say this is the T saturated at 35 bar and T saturated at 0.04 bar. So, let us recall that from the steam table you refer saturated pressure table. So, we can say at 35 bar, which will implies T saturated at 35 bar will be 516 Kelvin, and second one is condenser pressure, that is 0.04 bar. We can say boiler, condenser. So, this here T saturated will be 29 degree centigrade. Now, let us find out what is the states point. We require information of H1, H2, H3 and H4. So, these 4 numbers we require. So, for this we have to get the data from the steam table. So, let us see that 35 bar, again we are referring saturated pressure table. So, we can say H1 as 1049.8 kilojoule per kg, and this is nothing but saturated liquid region, and H2 is nothing but saturated vapor regions. That number is 2803.4 kilojoule per kg, that is nothing but your Hg. Since this particular process, if it is entropy, so we say S1 is equal to S4 and S2 is equal to S3. So, we require the data of S1 and S2. S1 is 2.7253 kilojoule per kg Kelvin and S2 would be 6.1253 kilojoule per kg Kelvin. So, we got the data for at 35 bar and then similarly 0.04 bar we can get entropy, but the 0.3 and 4 as are in the liquid vapor regions. So, this information has to be get, we require the value of dryness fraction, that is X3 and X4. Now, to get half this X3 and S4, we can find out a relations which is S3, which is at 0.3 is nothing but S3F plus X3 into S3Fg, and this S3 is nothing but S2, which you have already data this. Now, what is S3? S3F is at this point. So, this data can be obtained for 0.04 bar and this number is 0.4226 kilojoule per kg Kelvin, and S3G also can be found out for this point, and this value is 8.4746 kilojoule per kg Kelvin. Then and similarly for S1 is equal to S4, and when say S1 4, that is S4F plus X4 into S4Fg. Here also S3 and SF, and here we can see S3F is equal to also S4F and S3G is equal to S4G. So, these two equations will give you the value of X3 as 6.1253, which is this, minus 0.4226, which is this, divided by 8.4746 minus 0.4226, which is this. So, this number will be X3 will be 0.67. Similarly, X4 can be evaluated from this entropy data, and this value is 0.27. So, at 0.3 and 4 we find these dryness fractions. So, this will give you H3F. H3F will be X H3F plus X3 H3Fg, and H4 will be H4F plus X4 H4Fg. So, this value by putting this number we say 1832.9 and this number will be 811.15. So, both are kilojoule per kg. So, basically we have got all these numbers. Now, it is easy to calculate turbine work. So, turbine work is H2 minus H3. So, this is 970.5 kilojoule per kg. So, all the data we know. Compressor work is H1 minus H4. So, this value would be 238.65 kilojoule per kg. Then Q in, which is H2 minus H1. This number is 1753.6 kilojoule per kg. Then Q out would be H3 minus H4. So, this number is 1021.75 kilojoule per kg. So, once we know this, we can calculate efficiency, that is W net by Q in. This number is 0.417. Then work ratio W net by W t. This number is 0.778, and SSC, specific steam consumption, that is 3600 by W net. By putting this number, we will get 4.92 kg per kilowatt hour. So, basically what we did, we have drawn this Carnot cycle, we found out its cardinal points, then from this data we evaluate the parameters like efficiency, work ratio and specific steam consumptions. So, this particular problem does not have process inefficiency into account. So, the next process, same problems, we are trying to incorporate the process inefficiency as in terms by recognizing it as isentropic efficiency for compression and expansion process. So, the calculations remains same, and now when you include this, how this cycle should look like. The cycle should look like in the manner that instead of a rectangle, so the expansion process goes in this manner and the compression process goes in this manner. So, we say actual process as 1 dash, 2, 3 dash, 4, and in between we have 3 and 1. So, 1, 2, 3, 4 is the actual the Carnot process, and without involving the component efficiency, and here with real process is 1 dash, 2, 3 dash and 4. So, for that we have to still rely on the same data, which is H1 as 1049.8, H2 is 2803.4, H3 is 1832.9, H4 is 811.15. So, this was obtained in the last problem from the steam table based on 35 bar and 0.054 bar. So, now we are going to put component efficiency for the compressor and turbines. So, for that things we have to recalculate turbine work. So, W23 dash is equal to efficiency of the turbine into H2 minus H3. By putting this number, we will get this is 728 kilojoule per kg, and similarly for pump or expander work, we say it will be W4 1 dash. Here this, since it is a work input, so this number will be H1 minus H4 divided by compressor efficiency. So, this number becomes 318.2. So, precisely this number is higher than the previous value. Then we require Q in. Now, for Q in is nothing but your H2 minus H1 dash, but we do not know H1 dash. To do that, we can calculate this H1 dash from this actual turbine work, that is W4 1 dash plus H4, and this number is 1129.35 kilojoule per kg. So, based on this data, now we can calculate efficiency, that is W net by Q 1 dash 2, that number is 0.24. Work ratio W net by W turbine. So, this number would be 0.56. SSC is 3600 divided by W net, and this number is 8.78 kg per kilowatt hour. So, if you see our previous data, the efficiency was 0.417, work ratio was 0.778 and SSC was 4.92 kg per kilowatt hour. So, this implies process inefficiency have effects as what? Drop in cycle efficiency, drop in work ratio and increase in specific fuel consumption. So, ideally speaking, that we should keep this process inefficiency or in terms of irreversibility to as minimal as possible. So, with this I conclude this lecture. Thank you for your attention.